Welcome back to the deep dive. Today, we're not just looking at, small incremental gains. We're diving into what might just be the conceptual glue that finally binds the world of huge language models to computer vision. Our mission today is to figure out if visual AI can truly learn to, well, write an image.
Right. And the hook is really powerful.
Mm-hmm.
Can the generative pre-training that made modern LLMs so successful actually be ported over to vision?
It seems like a fundamental shift.
It is.
Yeah.
Traditionally, vision models were all about outputting these static features, these representations.
Yeah.
This new approach completely changes the goal. You're not just learning a representation, you're training the model to directly generate embeddings to predict what's next.
So it's moving from static analysis to something much more dynamic and generative.
Exactly.
Okay, so that's the big idea. But let's talk mechanics. The paper calls their technique Next-Embedding Predictive Autoregression, or NEPA. So if language models have words, or tokens, NEPA is breaking images into these visual patch embeddings. It's like giving the model a visual vocabulary.
That's a perfect way to think about it. And the nuts and bolts are surprisingly straightforward. The model just learns to predict future patch embeddings based on the past ones.
It's looking forward piece by piece.
Yeah, just leveraging that language model playbook to read an image in sequence.
Okay, but that feels like a huge architectural gamble, doesn't it? Predicting the next embedding, that's not totally new, but usually you need all this other heavy stuff like expensive pixel reconstruction or a complex contrastive loss to make sure the representation is actually good.
Right, to ensure quality. But they managed to skip all that.
So how did they get around it without sacrificing power?
Well, they borrowed two key ideas straight from the generative world. First is causal masking.
Okay.
It forces the model to read an image sequentially, say left to right, top to bottom. It can't peek ahead.
Got it. And the second?
The stop gradient, it's basically a technical break that keeps the target embedding stable while the model is trying to learn to predict it.
The simplicity there is really striking. When you strip away pixel reconstruction, you strip away contrastive loss. You're betting everything on just the quality of the prediction.
You are.
So what does that bet pay off? What do the benchmarks look like?
The results are seriously impressive. It really shows how effective this streamlined approach is.
Okay, lay it on me.
Using a standard transformer on ImageNet 1K, the ViT-B backbone hits 83.8% top one accuracy.
Wow, 83.8 that's really strong.
And if you scale up to the larger ViT-L backbone, it jumps to 85.3% after fine-tuning.
That's wild, but the real test for a model like this is transferability, right? How it performs on other different tasks.
Exactly, and they show it transfers really well to something like semantic segmentation on the 8020K dataset, which is notoriously difficult.
And that's hard because it needs a pixel-level understanding of the world, not just a broad label.
Right. So if this simple predictive model can do that, it confirms the embeddings it learned are genuinely powerful. It's building a real internal model of the world.
So connecting this to the bigger picture, this generative approach offers a simple, scalable, and maybe even a modality-agnostic way to do self-supervised learning.
Yeah, this core idea could be much, much bigger than just computer vision.
Okay, so let's bring this back home. What does this all mean for you? If this one mechanism, this prediction and embedding generation, can bridge language and vision so cleanly, what's next? Think about other complex data types, scientific simulations, maybe genomic sequences.
Or even just raw sensor data.
Exactly. Could this be the key to unlocking those worlds too? Something to mull over until our next deep dive.